Hello and welcome. This is Electricity and Magnetism, video part 11. Today I'm going to talk about magnetic forces on current carrying wires. So magnetic fields yield forces on current carrying wires. I'm just going to call it I, standing for current. So in the previous video, I talked about how a magnetic field would create a force on a moving charge, which would be given by this expression here. You take the charge and the speed of the velocity of the particle and take this cross product. This would give you the force equal to the force, which is part of what we call the Lorentz force. In the most general case, you have the electric fields as well. So you could add that term. But what we're interested in is in the second term here, QVB. Well, a current is nothing but charges moving along a conductor. So you expect a magnetic force on that wire as well. So here's your conductor. It could be any shape, but pretty much you have a current in it. Assume that you have positive charges moving in that direction. Now, your current carrying charges could be positive or negative. In a conductor, it's actually electrons that are moving in the opposite direction. But for our argument here, just imagine it was the positive charges, which would be going in the same direction as the current. All right. Then if you have an external magnetic field, let's say in this direction, we have B. So you would expect this force. How do you find the direction? You put your thumb in the direction of the velocity and index finger in the direction of magnetic field. These two could be at any angle except 0 and 180, but the cross product of the two will be perpendicular to both vectors, and that will be the direction of the force. So in this direction, in this case, the force would be this way on that positive particle. So this force is perpendicular to the magnetic field and also the velocity. Now imagine billions of these charges moving, which is the current. So you would expect a force on the wire. Now, the shape of the wire determines the direction for our current, since current has to be parallel to the conductor, and that will determine the direction of the force. So we need a vector. I is not a vector. Velocity is a vector. How about we consider an infinitesimal displacement along the current, call it, let's say, dl, and multiply it by the current. So this vector will be used in a cross product. So instead of a V, I'm going to use this. And the result will be the force. Since I'm only considering an infinitesimal displacement in the direction of the current, I'm going to call this dF. So if I want to find the total force on that conductor, I need to integrate, add these contributions from each dl. So the simplest case you can imagine, a uniform magnetic field and a perpendicular current. So using our convention from the previous video, let this cross in a circle represent the magnetic field that is going into the page. And we have a current which is perpendicular, call it I. So according to the right-hand rule, put your thumb in the direction of this vector here, IDL. So IDL points in the same direction as the current, remember? So it's got to be your thumb pointing up and index finger into the page. So the force will be to the left. Force will be to the left. Assuming I have magnetic field only in this region here, let's consider a rectangular plate, L, H. So this integration of df will simply give me this product times the length along the current, which is H. So the net force then here will be equal to this current times H times B, since B is uniform, remember? So you can carry it in out of integral. Whatever remains is just the integral of dl. That gives you H. The simplest thing you can imagine. Okay, so that's our strategy. For a given current, we look at the shape of the conductor, the wire. We determine the direction of the force by using the right-hand rule. Your thumb is IDL. Index finger is your magnetic field, and the middle finger will tell you which direction the force is. And depending on the geometry of this wire, you will evaluate the integral. That's the simplest case. You just multiply the length, but you could have a problem slightly different. How about, let's start with a straight wire, and then let's bend it. Let's bend the wire in the shape of a semicircle and then continue. All right, so let's say this is of length A. The semicircle has a radius B, so this is B here. And this part is C. And the magnetic field is again into the page. The uniform magnetic field into the page. And the current we have is moving from left to right, if you will. I here, left to right. Let's find the net force on the wire that carries this current, I. So we could divide this into three parts. The first part, A, and okay, let's name this A, B, part A, part B, and part C. Now, part A and C is just like the previous case, where we simply have a straight wire in a uniform magnetic field. So the length along the wire is what we need. That is A in the first part. Let's find the direction. Thumb in the direction of the current, index finger in the direction of the magnetic field. It gives you a vector pointing up. So the force will be pointing up. Let's call it FA. Similarly, in the third section, the force will be up, Fc. So Fa is I current times the length along the wire, A, times the magnetic field. Similarly, Fc would be I C B. What about the middle part? We have this wire bent into a semicircular shape. So we have to now be careful and determine what our DL is. Maybe we didn't need it in the previous parts, but let me just draw it anyways. So DL would be here, over there on the right hand side. DL is pointing to the right. DL has to be parallel to the current, remember? So if I pick a point here to find the direction of DL, I would consider the tangent line here, the line tangent to the circle. DL would point in that direction. DL. I'm exaggerating. I mean, it's a really small size vector, infinitesimally small. So this point here is B away from the center, obviously. So the radius and DL are 90 degrees apart. So let's call this angle here phi. All right, if that angle is phi, what else do I need? I need DL. So DL will be obtained by moving theta just a little, by an amount, d phi. But we're talking about an arc length, not just an angle. So I need to multiply that d phi by the radius, b. So DL in magnitude is actually b times d phi. Okay. I mean, my phi is going to go from 0 to 180 degrees, or pi, if you will. Pi. The current is in the direction where phi decreases. So, I mean, let's just think in terms of the absolute value. So this is nothing but the length of the vector DL in that sense. Okay, so if I multiply that by the magnetic field. Now, remember, magnetic field is into the page. So it doesn't really matter what direction your DL vector is pointing at on that plane, because any vector on that plane will be perpendicular to B anyway. So we don't worry about the angle between DL and B, because that angle is 90 degrees. So in this expression here, I DL cross B, the magnitude here would give us I DLB sine theta, not to be confused with R phi, that's something else. By theta, I mean the angle between DL and B, which is just 90 in this case. Always. No matter what your phi is, theta will always be 90 degrees, so sine 90 is 1. Okay, so that was the magnitude of the force. What about the direction? So right-hand rule again. Put your thumb in the direction of DL, index finger in the direction of magnetic field, and the middle finger shows you which direction force should point at. This is your force. Let's call it DF, because we're only interested in DL right now. DF or DFB and index B, because we're in the middle section. Okay, so this way, DFB is still perpendicular to the magnetic field being on that plane, but it is also perpendicular to the DL. So as DL goes around the semicircle, the force will change direction as well. For instance, if you're on the left-hand side, somewhere here, this would be the direction for DF, since DL would be in the tangent direction, like that, etc. So, but this gives us an important clue. On this plane, we have the horizontal components and the vertical components. If your force in the middle section is on the part where phi is less than 90 degrees, it will have a positive horizontal component to the right. If that angle phi is greater than 90 degrees, that component will point to the left. So here's what I'm talking about. Consider this vector on the left. You would have a horizontal component and a vertical component, right? Just boxing that DFB. And then here, if you draw that box around it, draw a box around it to determine the coordinates. Oops, I didn't want to make it that. Okay. This is the X component. This is the Y component. Now, there's a symmetry here. You have forces on the right and forces on the left. And the horizontal components will cancel. This will take care of that. But the vertical components will add. Okay, so for the middle part, when you integrate that df, you have to think in terms of the horizontal and vertical components. The horizontal components will add up to 0. And you can prove it easily. How? Just integrate this. So we have what we should put in an integrand here. So I think in the expression here, I forgot to put this little b, which would be the radius, right? No, the b is inside dl, sorry. So let me just erase that. I'm going to put it now in the integral here. So integral will be from 0 to pi, and dl is nothing but b d phi. Remember the arc length? So if this is d phi, this is b d phi. Anyway, so IB d phi times magnetic field times sine theta, which is just 1. But the horizontal component needs the angle now. So let's determine that. So if this is phi, then this is also phi. So we need cosine phi there. Cosine phi. So this will be equal to I B integral of cosine phi d phi, which gives us sine phi. And if you plug in those limits, 0 and pi, each limit will give you just 0. So the answer is 0, okay? That's what we expected anyways, because half of the time, they point to the right, the other half, the x component will point to the left. What about the vertical component now? The y, if you will. This was the fx. Same idea, integrated. I, b, b. But what are you integrating? You're integrating sine phi, because the vertical component will need a sine. And the integral of sine phi is negative cosine phi. From 0 to pi, and this part will give you cosine pi minus cosine 0. In other words, negative 1 minus 1. -2. There's a negative in the front, so it is +2. 2IB. That is the net force on the semicircle. Okay, so on the wire, then, the net force, which is FA, FB plus the force in part C. So let's remember what we found in the beginning. FA was IAB, and then ICB. So let's write those here. IAB, and then C, B. In the middle, we have now 2 I's times B. In other words, I times A plus 2B plus C times B. So this is the force on a wire shaped like this, where this is A and the diameter is 2B, and this segment is of length C, and the net force will be upward if the magnetic field is into the page. But look at this, A plus 2B plus C. That is nothing but the distance from this end to the other. So if I use a straight wire instead of a bend wire, a straight wire with the same length, that would be exactly the same force. That's what we saw in the beginning. So by bending the wire, I didn't really achieve greater force, right? Okay, so that's just one example. Let's try more examples. Let's say, okay, we started shaping these wires into the shape of circles and all that. So what about a loop now? Let's just make a full circle, right? So let me try to draw here I'm going to try to draw this in 3D, so hopefully it'll be okay. So this is a loop. The current goes like this, a loop. Okay, don't worry about how to realize this. Okay, you probably will need resistors and batteries, and don't worry about it. Just imagine we have a current, which is in the shape of a circle. In real life, probably you would just cut the cable from here and then connect it to a battery or something. But this is our current, I. Now I want to find the force on this. Of course, I need magnetic fields. So let me try to draw magnetic fields, which are lines that will enter this region from the bottom. So I'm going to try to draw it in 3D like this. So and this could be because of a simple magnet right below it. Why not? So magnetic field lines are always closed lines, loops. So it's just a representation. I can try to give you the full picture if I zoom out or something, but let's place the magnet. The magnet could be like a cylinder itself, like this. This could be your magnet with the north and south poles. This could be your magnet, which agrees with the direction of the magnetic fields that I just drew. So we don't need them, but let me just show you one of them. Maybe this line here, we could just draw like this. And then it's going to meet the other end like this. All right, so imagine this happening for all other red lines there as well. So these represent the magnetic field here, B. Okay, so according to this relation, dF equals I dL cross B, we expect a force. So how do we do that? Let's decide what dL is. dL is an infinitesimal displacement along the current. So right here, for instance, right there, we're talking about a dL that is going to look like this. That's your dL. At that point, the magnetic field is pointing upward, not directly up, but with an angle. Okay, with an angle means an angle it makes with the horizontal. So if this is the plane of that loop, and yeah, okay, so this is the horizontal line here. There's an angle here. That's your phi. All right. But the angle between dL and B is still 90 degrees. And that's due to the symmetry of the cylindrical magnet. If you have a cylindrical symmetry, it doesn't really matter what angle you're looking at. And if you align this properly so that the loop, the current carrying wire is aligned so that its center matches the center of the magnet, you have a certain symmetry. So let's call this radius R here. This is R. But magnetic field will be in magnitude uniform along the loop. So here it will point, yes, in this direction, which is still phi above the horizontal, but its magnitude will be the same because of the symmetry. Okay, I hope you're visualizing this. You're looking at this plane and the loop from above, okay? So if DL is 90 degrees at 90 degrees with the magnetic field over there, it'll be the same here. So DL is pointing this way, and then the angle between B and DL is still 90 degrees. So sine 90 is still 1. So there won't be any sine factor there. But we need to find the direction of the force now. Use the right hand rule. DL, thumb, B, index finger, and this will give you DF. DL, B, F would be a vector pointing below the horizontal line. Let's use green to show that. So right here, DF point this way, which would make 90 degrees. So DF is perpendicular to B and also perpendicular to DL. I hope my picture here is showing that. So here, right there, this is DF. Okay, so looking from above, DF would be radially outward. So top view. Top view, here you have the plane, the circle, or wire. And you could even draw here the horizontal components of the magnetic field. That would look radially outward, right? These are B horizontal. And DLs would be like this. Those are your DL vectors. And DF would have horizontal components in the same direction as magnetic fields horizontal. Okay, because of the symmetry. So that's top view. The side view, if you look at this from the side, what you see here is, here's your loop. You're only seeing from one end to another, so it's just a line, okay? So B is like this, and like that on the other side. And the vectors dl, on the right-hand side, it's going away from you, so this would be dl. And on the left-hand side, it's coming towards you, so dot in a circle, that's your dl. But I really want to draw the df. So df will be perpendicular to B, like this. On that side, like that. Okay, so let's check the angles now. Phi was the angle between B and the horizontal, which makes this also equal to phi, since B and DF are perpendicular. So DF will have two components. DF sine phi, that will be the horizontal component, and DF cosine phi, which is pointing downward, that will be the vertical component. Now, if you compare right and left in the side view, obviously those horizontal components will be canceled. Imagine this for every pair along the circle. Those two components will take care of each other. The goal is to find the net force. But the vertical components, since they're always pointing downward, they will add up to give us a net force, which is dF cosine phi. So all we have to do now is to integrate this. Now, when you're integrating along the circumference. Therefore, you need the length of dl, which corresponds to this angle here, call it d theta. And theta changes between 0 and 2 pi, 360 degrees, right? So what we have here is integral of I dl, which is r d theta, and we need b there. That's in the force. That's in the force. But we now also need the cosine phi factor, because we want to find the net force. All right. So the only theta dependence is here, which will give us 2 pi. 2 pi I r b cosine phi. This will be the net force, which is pointing downward. Okay, so there will be a net force on this loop, which is going to be downward. Now imagine you had not one loop, but 2 loops. So you will be integrating from 0 to 4 pi, if you will. Okay, 2 loops. You're basically multiplying the force by 2, or if you can add more, 100 turns, which would only make the force greater at the end. So we call these things coils. All right, coil. And they are used a lot, just to increase the force and other things. Now, but these two attract each other, at least I mean, I should say there's a force on the coil now, but we'll see in a minute that this is actually more generic than that. By letting a current run through a coil, we're actually creating a magnet to ourselves. These are artificial magnets or electromagnets, as they call it. So what we really have here is the interaction between two magnets. Now, in this picture, if you have the loop here pulled downward, it's as if you have two magnets on top of each other. This is the original one. And now we have another magnet on top. If this is going to be attracted, this side should be south, and this should be north pole above it. Okay, so this is not our chapter right now. The chapter we're working on is only about forces. In the coming chapter, we're going to see how magnetic fields will be generated by currents. And this will hopefully make more sense then. But for now, I can tell you right away, this looks like a magnet with its own magnetic field. So you will have a magnetic field also like this, up, down, here it is. So we're gonna define a quantity called mu. We're going to call it the dipole moment. It'll be a vector. It'll be a vector, and it will be proportional to the area of the loop here. So in our case, the area is pi r squared. So if you multiply this by the current, I times A area, this is what we're going to call the dipole moment. Now, the reason we need this vector is it's going to make things so easy if you think about loops which are not horizontal, but they're with an angle. So a loop like this is represented by a mu vector, dipole moment, up because of the current running this way. If I rotate that loop, since mu has to be perpendicular, it has to rotate as well. So it's perpendicular to the plane of the loop here. Okay. Hi. And you can use another version of the right-hand rule to remember which way mu points at. Just curl these fingers, 4 fingers, wrap them in the direction of the current, and the thumb will tell you the direction of the dipole moment. Now, in order to understand this better, I'm talking about the one with the angle. Let's use a very simple loop. It doesn't have to be a circle. Let's just use a rectangular loop. Let's place the rectangular loop in a uniform magnetic field and see what happens. So we can do it in many ways. Let's take a magnetic field which is into the page like this, and the loop, which is now just a rectangle or square, let's say, a square. like that, with some current I. So the current is running counterclockwise. So the problem is force, right? How do we find the force? It's a uniform magnetic field, and we have straight wires, so we don't really have to worry about integration. That's why I picked a square instead of a circle. Not that it will be very difficult, but let's just keep it simple and different. So we basically have DL pointing this way, to the right, up, here, left, here, downward. DL. So we have 4 segments, obviously. Each has a length L. Let's try to see what happens in terms of force. So DL and B are 90 degrees, which is good. The force will never be 0 for each segment, but let's find direction. Put your thumb in the direction of DL and index finger in the direction of the magnetic field. So for the right-hand side, I already see that there will be a force inward to the left, dF. If I repeat that for the top section, DL to the left, B into the page, forces downward. I put an arrow pointing this way. Now DL downward for the left side, DL downward, B into the page, so the force is to the right. And if you repeat it for the bottom part, you'll find out that the force will be up. So what is the net force then? 0, right? Net force is 0. So each dF in magnitude would be equal to I times L times B. And since they're opposing in the horizontal and vertical directions, if you add them up, you get 0. So there will be net force. There won't be any net force. It will be 0 for this case. Okay, not that exciting. Let's change the magnetic field. Let's keep the loop the same. It's still a rectangular loop. But still a counterclockwise current. Okay, let's just change the magnetic field. Oh, that's all. So how about a magnetic field which is up, pointing up? It's a uniform magnetic field. Okay, magnitude is the same everywhere. It's pointing up. Now the DLs are the same. Here, these are my DLs. Now, the angle between the DL and magnetic field, because I need it in this cross product, that is now changing if I go from one side to another. Basically, if I'm on the right-hand side, DL is up, but so is the magnetic field. The angle between the two is 0, and sine 0 is 0. So there won't be any force on this portion, on the right portion of the square. Similarly, on the left, the angle between DL and B is 180 degrees. Therefore, sine 180 is 0, no force. The only force we're talking about is the one on the top and the bottom. So DL to the left and B is up. The force would be into the page. For the top section, force is into the page. In the bottom section, DL to the right, B is up, and the middle finger coming out of the page. Now this is interesting. The net force is still 0. But the interesting part is now we have a torque. A torque. This will rotate if it is free to rotate. Why? Let's look at this from an angle, from the side, let's say, side view. Here's our observer looking at this from the right direction. So in that view, side view, all we see is this loop. I'm still going to use the same color here, green. And magnetic field is still up. That did not change because I'm looking at this from the side. Magnetic field is still upward. The current, I can only show the current in the top and bottom parts, which is not really the parts which are the parts I need. I don't care about the side one. So on the top, since I'm looking from the right, the current is away from me. So dl is a vector pointing into the page. This is dl. In the bottom part, dl is coming towards me, so it's coming out of the page. That is dl. Okay, so let's apply the right-hand rule again. dl in the bottom part coming out of the page. B is up. The force will be to the left. Please make sure you do this when you watch the video, okay? So the force will be to the left. Repeat it for the top part. dl is into the page. B is up. Force will be to the right. F. Okay, this is the front view, that's the side view. But what happens now? If this was L, the length of the thing was L, pick this point in the middle, call it P. You have half of that here and the other half at the bottom. And the line of force, line of action is this. Here's the pivot point. The distance between the two, the shortest distance, is by definition the lever arm, L/2. So you have a torque from the top and the bottom part, torque. The magnitude of this torque from the top part is simply F times L/2. But in the bottom, you also have the same, so it's 2 times that. Okay, so the rotation will be a clockwise rotation, which means the torque vector, using the right-hand rule again, the torque vector is into the page. Torque is into the torque, tau. The letter tau is for torque, is into the page. Or monitor. Now this torque will be present until it finishes the rotation by 90 degrees. So once it rotates 90 degrees, now it's still the side view, right? So now it's going to be perfectly horizontal. Force will be left and right. It's still canceling each other, and that did not change, but the torque will also be 0 in this alignment. What about an angle between the two? So okay, so my loop will be now rotating this way. Remember, spot rotation under the influence of this torque. The forces are still this way. By the way, when you have this configuration now, you will also have forces on the other sides as well. I'm going to show you in a little bit, but they will not contribute to the rotation. They will not contribute to the rotation. So here's why. So you have now a current that goes along the loop like this. On the side which is closer to your eyes, right? This is your current, which means DL is in the same direction too. But now the angle between DL and B is not zero anymore. So you do have a force. How do you find it? You put DL, thumb, and B. The force comes towards you. So let's add a front view for this one. Front view for this one, this part, where you have some rotation between 0 and 90 degrees. In that case, your square root looks like a rectangle because there's rotation, right? So what you have now is forces to the right and to the left. Besides the other forces, which are rotating them, that's into the page, coming out of the page, yes. But now you have the forces in the opposite direction, in the horizontal direction, but still, I mean, not only they do not contribute to the rotation, they also cancel each other. The net force is still zero. Net force is always zero. Whenever you have a loop inside the magnetic field, the net force will always be zero if it is a uniform field. In the previous problem where we had the cylindrical magnet and then the varying magnetic field around it, in that case you would have a net force. It's a different issue, right? Okay, so all right, so when we have rotation, there's a torque here. So let's find the torque then, just like we did here. But now we gotta find the new lever arm. So from here to there, that's the new lever arm. So let's call this angle here theta. The new lever arm will be L over 2 cosine theta. Okay, so F times L cosine theta over 2 is a torque from 1. There's also another one here, so multiply by 2. That will give you the torque for an arbitrary angle theta. So obviously when theta is 0, cosine 0 is 1, you have the maximum. When theta is 90 degrees, cosine 90 is 0, therefore you have the 0 torque. So that matches this observation on the right-hand side. Let's apply this to that magnetic dipole moment we just saw a minute ago, mu. So let's try to find the direction of mu first. Using the right-hand rule again, wrap your fingers in the direction of the current. The thumb will tell you which way mu is pointing at. So in this view, this is the side view. When we have the current, now this arrow here represents DL, therefore the direction of the current. That's the side which is closer to us. On the other side, it's going down. So if you curl your fingers in that direction, mu is pointing this way. Let's use red. Mu is pointing this way. All right. Now, can I find the direction of the torque from just the direction of mu? That's going to make life easier because I don't have to worry about each side and all that, right? There are 4 sides. What if I have multiple sides, more than 4? I don't have to go through each side to determine which way the torque is. I can just look at mu and B. So I can consider the cross product of the two. Mu cross B. Okay, use those 3-finger right-hand rule again. The first vector is mu, the second vector is first finger, thumb is mu, and index finger is magnetic field. So mu cross B gives me a vector which is now pointing into the page, just like I figured. That's the direction of tau. Okay, mu cross B gives me a vector into the page. What about the magnitude of tau? I mean, don't we need a sine factor here? So the angle between mu and beta, magnetic field, sine phi. Which angle is this? The angle between B and mu. This is phi. And that's only the other angle here. So phi plus theta is 90. So it matches here. See, these twos cancel. And then I have cosine theta, which is nothing but sine phi. So I have here FL sine phi. So what is F? Right? F was, we found what F was. It was IL. The angle between DL and B. We're talking about this part here, and that part was 90, so there wasn't any sine factor there. But we did have B times I times L for F. There's another L here, which makes L squared, okay, times sine phi. Now, if you compare this torque expression to what we have over here, okay, let's just circle the things we have in common. Sine phi, B, what is left? IL squared, or I times area. That's what mu was, right? Remember in the beginning? Let's go up a little bit here, where we defined mu. It was the current times the area of the loop. So that agrees, okay? So from now on, whenever you want to find the torque for a given loop of current, don't worry about the geometry that much. As long as it's a loop, it's going to have a dipole moment. Let's say the loop is shaped like this. It's still a loop. Just imagine your fingers going around the loop like this, and the thumb is the vector which is perpendicular to the plane of the loop, in this case coming towards you, right? This is the direction of the mu. Or if I try to draw this in 3D, you have this plane here, okay, and the loop is a pentagon like this, okay. Now, it could not be even a regular pentagon, and it's arbitrary. Now imagine you find the force on each segment. You know, it's a lot of math there. Don't worry about it. Just curl your fingers in the direction of the current. This green arrows represent the current, right? So the magnetic dipole moment will be this way, which is perpendicular to the loop. Okay, so if once you know where mu points at, it's just a matter of calculating the cross product. So mu cross B will give you the torque. Okay, so that has the angle between the two, which will be sine of the angle between the two. If that angle is 0 or 180, torque will be also 0. So going back to that very first example, one of the first ones, with the circular loop and this one. Mu is pointing up. Mu. And imagine the magnetic field just in the middle. That's also pointing up. So think about it, by the way. I mean, even the center magnetic field, it feels like it's just a straight line, but that is supposed to come back to the south pole to complete the loop. Magnetic field lines are always cycles like that. Anyway, it's up and mu is in the same direction. So torque is zero, right? There's no torque. But once you rotate this, then you may have some torque. Okay, so that's the idea behind magnetic force on a current carrying wire. I just showed you this example here with the band wire. Now, so now that you know how to do loops, maybe you can try this as the homework. A loop in this shape. Okay, try magnetic field. Put a magnetic field like this first. And then try a magnetic field, maybe 90 degrees to that, into the page, all right? Find the total force. Okay, this many examples, I think, is enough about magnetic force on wires. So now we have an expression for torque as well. This is the basis of electric motors. Okay, the DC motors you can find in your computer's hard disk, for instance, work on this principle. Of course, in this case, you know, we have a rotation like this, and then you're done. You want to keep that going. So there are options of doing it. You either have to change the direction of the current, like our power lines or alternating current lines, or starting with a DC current, direct current, you can still change the direction in the loop by simple mechanical devices, like using brushes against, okay, so you can have a loop like this, rectangular loop. And you could have this middle part is your rotation axis, let's say. So this could be touching against the two brushes where you connect your battery. But when you rotate it, those wires will rotate as well. So there are ways to change the direction of the current in a loop. So you can have a continuous rotation. Okay, that's the basis of all DC motors. And Nikola Tesla came up with induction motors, which eliminated the use of brushes. So you get rid of friction. But that's technical. Let's not worry about the DC motors. You can read the book section about motors, learn more about them if you're curious. Let's just do magnetic flux, and then we'll be done with this chapter. Oh, there's also Hall effect. So let me talk about Hall effect first. Okay. Now, Hall effect is when we have electric fields as well. So here's how it goes. Let's say you have this conductor here in the shape of a rectangle. Let's make it simple, like a prism, all right? So we want a current now that goes through this, right? So let the current be up. Let's call this L, this side T, and then this side H. And let's say we have a current that goes through this conductor. Okay, somehow we have a current. And we're going to apply a magnetic field now through this. Let's say the magnetic field is from left to right, if you will, like this. It's perpendicular to the plate. Let this be your magnetic field, P, and the current is up. What is a current anyways? I mean, we're talking about the direction of positive charges, but in the conductor, it's really electrons, negative charges, which are moving in the opposite direction. So let me draw an electron here in the opposite direction. So what color? Let's use yellow for an electron. Let me draw it here, electron. It's a negative particle. It's actually going downward. Remember the drift speeds and all that discussion? That's what we have here, the vector, VD, pointing down, electron. So what about the force on that electron now? Since it has a velocity and a charge, the charge of the electron is QE, and we have the drift velocity, VD. So take the cross product of V with the magnetic field and multiply it by Q. That gives you the force on that electron, right? So the direction of the cross product is easy. Put your thumb in the direction of velocity, downward, and index finger in the direction of the magnetic field. Then the force would be this way. But remember, it's an electron, a negative number. Charge will be a negative number, so you're going to flip that product. So once you determine the direction of V cross P, don't forget to flip it 180 degrees. And 180 degrees, it'll be the other way. So the force, the actual force on the electron will be this way. I'm talking about the magnetic force, right? FB. FB, magnetic force will be to the left, or that side, if you will. Again, V cross B gives you the cross product. V is down, V is this way. Please do this when you're watching the video. And the middle finger shows you a direction, but you're going to flip it because it's a negative particle. This way, the magnetic force on the negatively charged particle will be to the left, which will be acting on all the electrons. So this side will become negative now. They're going to be pushed to that side. This side, excuse me, will be all these negative charges. Not all of the electrons. I'm talking about some of the free electrons. Now, if the left-hand side becomes more negative, that means the side, or opposite side, will be positive. The absence of electrons corresponds to a positive charge. Okay, are we good so far? You have negative charge pushed that way, and they accumulate there because more and more electrons will go there. There's no more room to go, and they're going to pile up. Bunch of negative charges and a bunch of positive charges. But that's only half of the picture. Because once we have these charges separated, now we have a reason for an electric field that goes from positive to negative. Okay, what color? Green. From positive to negative electric field. Okay, so we have the electron here. To the left, we have the magnetic force. But since the electric field is in the same direction, there will be now an electric force. Right? Remember this formula? Fe is equal to charge times electric field. If Q is negative, Fe is negative, a negative number times electric field, which means in the opposite direction. So, how do these forces compare? Well, as long as Fp is greater than Fe, you will have a net force in that direction, and the electrons will continue to move in that direction. And more charges means greater electric field, so Fe will catch up after a while, okay? So whenever these two are equal to each other, the net force will be 0. If the net force will be 0, there won't be any further accumulation. Whatever you have is what you have. And then the current will just take care of the rest. Electrons will not be deflected anymore. But those charges will stay there. So when these two forces are equal, meaning Q electron charge times drift velocity times B, remember these were perpendicular, so sine 90 is 1. That's equal to the electric force, which is QE times E. When this happens, when net force is 0, these two are equal to each other. Okay, if that happens though, we still have voltage difference between the two ends, and that's the whole idea. So if you put a voltmeter, connect the voltmeter between these two sides, you will measure a non-zero voltage, and we're going to call this Hall voltage. Hall voltage, VH, if you will. Hall. We're going to call this Hall effect. The Hall, named after the physicist who came up with this. All right, that's actually a device you can use to measure the strength of the magnetic field, okay? And I'll show you how. So that's the voltage difference you would measure between those two sides. Let's try to find an expression for that. Now, the electric field will be uniform, therefore, the electric field multiplied by the length in that direction, which is L, will be equal to this VH, fine. Current is I. Now this current, if we write this, if you go back to the chapter where we first saw the current, we found an expression. Remember that? It was N, which stands for the number density of charge carriers. In a given volume, how many free electrons do you have? Okay, it changes from material to material. So it's a density, number density. If you multiply it by the area, so we're talking about the cross-sectional area here for the current. And then you have the drift velocity and the charge. This is how you write the current, right? So A is L times T. So I'm going to take the electric field. No, I'm going to do this. I'm going to see here I have the VD times QE. You see that? VD times QE. So that's equal to current divided by N times A. I'm going to take that and plug it in the first equation. So here this will be written as, instead of V times Q, I'm going to write I over NA times B is equal to Q times E, and I'm going to write Q here. Instead of E, I'm going to write VH over L. Hall voltage over L. Okay, so VH then, let's go back to black. VH then is equal to 1 over N times Q times I times L times B divided by area. Okay. Now I could call this number in the front something else, because that'll n will vary from metal to metal. Let's call this the Hall constant. Hall constant, or what do they call it? It's a constant, R. Let's just call it R. And L was, A was L times T, right? So if I plug LT here, L's will cancel and T will be left. So I can write the Hall voltage as this constant R times I times magnetic field divided by T. Okay, so T is nothing but the dimension of the conducting piece in the direction of the magnetic field. That was T. So either use the original version, then you have to use the length across the magnetic field. Okay, I think it's the second one is easier because you don't have to worry about H, do I rotate it or what? So don't worry about it. Just use this formula here. This formula is actually good. Just use this to determine what the Hall voltage is. Experimentally, since you can directly measure the Hall voltage, and you know how much current you're giving to the system, and T is a given number you can measure, you can actually calculate B. Or you can use this as a magnetometer, okay, a magnetic field strength tester, or magnetic field, you can use to measure the magnetic field, basically. Okay, so all you need is that small conductor at the end of a probe, like this pen. You can put that probe in here, and you can bring it close to a magnetic surface, like a magnet, and then you can take the reading from the other side. You just have to know how that voltage changes. Okay, you gotta be able to measure that voltage. So that's Hall effect. And the picture I showed you here works fine for electrons as your charges. But in some conductors, like semiconductors, you can also consider positive charges. A current is indeed the motion of positive charges. There are these holes, they call it. If you go into advanced topics in material science and physics and electrical engineering, you'll be working with semiconductors. And I don't know, maybe plasma physics, also will deal with these. So in those cases, you have to determine the direction where the charges move again, right? So if charges were moving up and they were positive, then put your thumb in that direction, and B is that way, then you would have the positive charges moving in a direction where the negative charges are right now, okay? It'll be the other way around. So you gotta be careful. You gotta find out what your charge carrier is. And for conductors and regular currents, it's always electrons, we know that. Okay, so that was the Hall effect. And finally, I want to talk about flux, magnetic flux. Now, the word flux, where do we know it from? From electric fields, right? Remember Gauss's law? Let's remember Gauss's law. Gauss's law was about the electric flux over a closed surface. The circle in an integral means closed surface anyways, but let me just write it to remember. We evaluate the integral E dot product dA, and this would give us the charge enclosed divided by epsilon 0. Okay, in general, for a given surface, the vector is the infinitesimal area vector which is perpendicular to that surface. I'm not going to go through this again. Just watch, I think it's part 3 or 4. Part 2, I think it's part 2. I explained this idea of flux. So you use the electric field in this Okay, to find the dot product there. So E dot dA gives you E dA cosine theta if the angle between the two is theta and all. So we know how to do it. I'm not going to go through this again. But I'm just saying we can apply the idea to magnetic fields. Why not? And we call it the magnetic flux. So magnetic fields will also result in fluxes. So this is your area, and you have a uniform magnetic field, which is perpendicular. Okay, the simplest case you can imagine. Just multiply the two. B times A will give you magnetic flux, letter phi. Okay, but I'm more interested in Gauss's law for magnetic fields. Why? Because on the right-hand side, we have this enclosed charge. So what was Gauss's law? You had this charge here, Q, and then you pick any surface around it. Doesn't have to be a ball, it could be any shape. If you're able to evaluate that integral, all you find is the charge inside divided by epsilon 0, the constant. And if there's no charge inside, the flux on a closed surface for electric field is 0. I even showed an example. I don't remember. It was a rectangle, triangular prism, I believe. Here, what happens with magnetic field is, since it's impossible to obtain a pole by itself, a monopole does not exist. In other words, magnetic field lines are closed lines, loops. You don't have magnetic field starting from a point, ending on a point. It's impossible to isolate a single pole. Therefore, the right-hand side will always be 0. Okay, will always be 0. So this is an important result. Let's just write it down. B dot dA is always 0. So, very simple example. Let's say you have a uniform magnetic field and a cylinder is your Gaussian surface. These two are equal areas, base and top. The dA in the formula is up for the top, and it's pointing downward for the bottom. So whenever you evaluate the integral, B dot dA, it'll be a positive number for the top, but a negative number for the bottom. So from the top, let's call it the flux from the top, will be equal to just the area. We're talking about a uniform magnetic field, area times B. But the bottom part will be negative A times B because the angle is 180 degrees, the angle between B and dA. So you add them up, you get 0. It's almost trivial, right? Now what if the areas were not the same? Meaning, what if you had a truncated cone, this capsule shape thing, you know? So obviously this area here is less than the bottom area. Let's call it A2. And you can still have a uniform magnetic field, doesn't matter. So in the top, you would have, did we call this A1? Yeah, you would have B times A1 as your top. And the bottom part, you would have B times A2, which is greater than B times A1. So how do we, negative, I'm sorry, this will be negative. Negative B A2. So how come Uh, the total is still 0, but now dA on the sides is pointing this way, or here, that way. Which means the angle between dA and B is neither 90 or 0, which was the case for a cylinder. For a cylinder, dA on the side was 90 degrees. They were cosine 90, 0. You didn't have any contribution from the sides for a cylinder. I forgot to mention that. But now you will have. Therefore, you will have a flux, magnetic flux, from the sides. So if you add phi top to phi sides, you'll get a number, and that number plus phi bottom will give you 0. Okay, so using this, you could come up with interesting things. Let's say you have a vase with different, okay, like something like this, a vase. Okay, I could say, hey, there's a uniform magnetic field, 1 Tesla, which is up or down, doesn't matter. And the top area is 10 centimeters squared, bottom is 20 centimeters squared. Calculate the flux on the sides. Okay, if you don't remember that the net flux, sorry, the total flux over a closed surface is 0, then you would worry about, hey, how do I integrate this function, you know, because dA now changes. This dA is horizontal, now it's with an angle. I mean, I don't even have the form here, the mathematical form. How do I integrate? You don't integrate. You know that the sum is equal to 0. So you just find the top and the bottom and subtract that from 0, and you get the flux contribution from the sides, okay? And if you want to really do some math, pick a shape which is not as simple as a cylinder, but still not too complicated, like a pyramid maybe. So let's say this is the basis of a pyramid with 4 sides like this. It's a regular pyramid. So you could be working with a side 10, 10, then let's say the height is 7, something like this, which would make, of course, it's 90 degrees here. And the magnetic field is, let's say, up. B is 1 Tesla. By the way, the unit for flux is Tesla times meter squared, or the name for it is Webers. That's unit for flux. Okay, so try this as a homework, okay, the pyramid. So what you need is, well, the base is easy. That's going to be n negative 100 times 1 Weber, right? Because dA is pointing downward and the area is just 10 times 10, 100. But the sides, you have to now calculate the area, of course, the area of this you multiply the area by magnetic field, and you have to also consider the angle. So you'll need this middle part here to find the angle here. So the angle between dA and the magnetic field, call it phi, will be this angle phi here. So you got to find the cosine of that by dividing this side by hypotenuse. You can find it easily. So, and you multiply that flux by 4 because you have 4 sides. So you add them up. What do you get? You get 100 Webers. You can do it. It's not too hard. Just use the basic Pythagorean theorem. And then the bottom You have 10, 10, 10. So this is square root 2 times 10, or half of it is 10 over square root 2, which is here. So from that and 7 height, you could calculate this side. There's another triangle here, right? So if the base is 10 over square root 2 and the height is 7, you can calculate this side, call it a D. And this is D. This is also D and 10. So you would have the area this way. This area is 10. This is D. The height would be square root D squared minus 100. So you find that number, and then 1/2 height times base gives you the area. Multiply the area by 4. You have 4 sides. Multiply the area by 4 and that number by the magnetic field, and cosine phi, which can be found by dividing this number by that. And therefore, if you do all that, you get 100 again, because negative 100 plus positive 100 should give you 0. Okay, so that's the end of this chapter. In the next video, I'm going to talk about sources of magnetic field. How do you find the magnetic field starting from a current carrying wire, things like this. Okay, we have the Biot-Savart law and Ampere's law for certain symmetries. You can apply Ampere's law. But that chapter will be about generating magnetic fields. And after that, we're going to start changing the magnetic field. Changing in time, and see what happens after that. By the way, this example here with the uniform, okay, that's not always the case, right? I mean, you may not have a uniform magnetic field to begin with. Now, what if you have that cylindrical magnet, magnetic field lines going like this? So if you pick a cylinder here, or any object for that matter, but to keep it simple, let's pick something like this, a weird shape. Why? Because I want the magnetic field to be parallel to the side this way, so that I don't deal with that. I only have to worry about the top area and the bottom area. And you may say, okay, hang on, this area is, okay, A2 greater than A1, which is fine. So how do I get the same flux from the top and bottom so they add up to 0, you know? Well, you can, because remember, as you move away from the tip of the magnet, the lines are diverging. So you don't have that many lines per area, which means the field strength is low. So here, if you call it B2 and here B1, B2 is less than B1. Okay, so by multiplying B2 by A2, you obtain a flux. Of course, B2 is not a simple multiplication. You have to integrate it and all that. Okay, so, but whatever you get there has to do with large area and small magnetic field. If you go down in the bottom part, you have a stronger magnetic field, but smaller area. So they compensate, and the magnetic field, magnetic flux, if you add them, you should be still getting 0. Okay, I'm going to stop here right now. Until next time, goodbye.